this is a general block of our op amps, and you can see, yeah, they are single stage op amp, two stage op amp, to at most three stage op amp. Even you have three stage op amp, we only provide voltage gain for the first two. Okay, and how about this stage? That is for current amplifier. Okay, we don't amplify the voltage for more than two stages. Why? Instability. Yeah, later, if I have time, I will show you this. More than two stages usually means unstable. Okay, yeah, it means even you apply very strong negative feedback, you still cannot make the overall system stable. So I need to warn you. One or two stages for voltage amplification should be good enough. No more than three. Okay, no more than two. Okay. Anyway, if you focus on the first one, the first stage, usually that is the so-called differential amplifier. Okay? Yeah. Again, according to the name, we would like to only amplify the difference instead of the common value. Okay, you have two input, differential input, V plus, V minus. We would like to only amplify the difference instead of the common value. Okay? And then for the second stage, that is so-called high gain stage, but differential amplifier will provide the most gain. And then, so for example, if you can amplify, you do a very good design, yeah, to get 5 order in amplification, usually 3 order for the first and 2 orders for the second. Yeah. And then finally, if you have this, then it is used to drive the load. Okay, it means what? Large enough driving current. Okay, that's it. And in between, as I mentioned already, we hope op amp can operate down to DC. So no capacitive coupling can be allowed. Usually, yeah, my output DC level, and how about your input DC level? Usually, they are not the same. So when necessary, we need to have such kind of DC shifter, level shifter. Okay? The same happens between second stage and third stage. According to Professor Allen's textbook, this is a very good classification for you guys to know first stage and second stage. How about third stage? Because third stage is for current amplification, if there's any. So we only focus on, I mean, according to Professor Allen's textbook, it only focuses on such kind of two-stage structure. More interestingly, you can see, never mind for the first stage or for the second stage, you can see we always convert the input voltage into upper current. Okay, that is the first idea you need to know. And then, how can you convert current back to voltage? Piece of cake. Because V equals IR, right? So we convert input voltage into output current. That is, yeah, that is for the first moment. And for the second moment, we convert I out with RO, right, to be V out. That's it. Okay. Why we need to emphasize on this? It means the gain for VI to IO, we call it GM, transconductance. Okay? The larger transconductance, the larger output current. And then the larger RO, the larger output voltage. So it means what? The overall voltage gain should be GM by RO. That's it. Very simple idea. To be a very good analog IC designer, you need to know this much easy to understand concept. How to increase your gain? If the gain is not good enough, then two major ways. Either you increase the transconductance or you increase the output resistance. But nothing is free. If you would like to increase it, usually it means very large transistors needs to be used. Okay? So to save money, usually we hope we can increase RO. That's it. Okay? If you can do, usually we increase RO. But again, to increase RO, for example, by cascading, right? You have one transistor for output, and then above it, another cascading transistor. Congratulations, you only double the device area by 2. But how much you can increase RO? 100 to order. I told you already. By cascading, we can increase the output resistance by 2 orders. That is really powerful. However, nothing is free. You need to pay for it. Pay what? Headroom. Exactly. Okay? The other example is, if you wouldn't like to sacrifice your headroom, you would like to increase GM by the same number. Oh, I promise you. You need to enlarge your input transistors by 100 times. Okay? So that is the power of cascading. But that is the good is also the bad. Only if you have enough supply voltage range. Only if your supply voltage is high enough. Otherwise, cascading sometimes is hard to apply. Okay? Yeah, anyway. Similar situation for the second stage. Again, we convert the input voltage into output current and then by RO to create the output voltage. GMRO, that is always the concept. Okay, but how to convert the voltage into current? Anyway, for the first stage, usually we have such kind of differential amplifier. Never mind, that is the classic one or modified one. Okay, yeah. And then how to convert the current into voltage, into output voltage? Usually we have current mirrors, current source as the load. Why? Because to get enough RO, in the past we have real resistor, okay? But to achieve 10K or even 100K, 1 mega ohms, it is really expensive. I mean, it is a really cheap area wasting. Okay, so gradually, especially for CMOS, we hate passive devices because they are bulky. I mean, they are really large. Okay, so how to get enough resistance but without sacrificing too much area? Active load. Yeah, use current mirror, current sources as a load. It is a very good idea. Okay, and this is the reason why I told you current source first instead of op amp. Yeah, we are different. Okay, and then so current mirror, current source as a load. But sometimes we wouldn't like to have too much gain. Then we can apply diode load. Okay, diode connected means the resistance is rather low. I mean, compared to current source or current mirror. But why? We wouldn't like to have such kind of high gain according to bandwidth. From the input to the output, if there's any kind of parasitic capacitance, right? According to mirror effect, if you look into the input, these capacitors will be amplified with this gain. Okay. So if it is 100, wow, it means what? Equivalently, such kind of parasitic capacitance will also be increased by 100 times. 100 times means what? As you know, right? Proportional to 1 over RC. The more capacitance or more resistance means the frequency, the bandwidth will be substantially reduced. That is what we hate. All right? So sometimes if you would like to expand your bandwidth, then you need to sacrifice your gain. Nothing is free, pay for it. Okay, either large bandwidth or high gain, but you cannot achieve both. That is really hard. Okay, that's it. And how about the second stage? Usually a common source, blah, blah, blah. So that is a very traditional one. You learn already from your microelectronics. Actually, all those, I guess, you learned already from your microelectronics. But we are exceptional. Yeah, we wouldn't like to teach you the same thing from your microelectronics. We would like to wash your brains, yeah, to get better understanding. Yeah, so how to design a Cmos Op Amp? Usually from the very beginning, you can choose the existed one. Choose one among all of them. Or you can create your own. Okay, you have two choices. Yeah, after, never mind, you choose one or you create one. The result is a new schematic. Okay, and then you need to do resizing. Okay, sizing. Usually, yeah, that is a noun, but you can make it as an adverb. Okay, so we call it sizing. Yeah, it means to adjust the size of the transistors. Okay, that's it. And not only you need to fine-tune the sizes, but also the biases. Yeah, it costs most of the design effort. It means most of the time actually is devoted to such kind of fine-tune. That's it. Yeah, but how good the result will be? Usually through the help of simulator, especially just like HSpice, iSpice, blah, blah, blah. Okay? But anyway, if you have much better understanding about the op amp, the circuit, then such kind of prior performance, yeah, will do a good help. Yeah, and if you do a good enough design, then we can do the layout and floor planning means for so many devices, where to allocate this, where to allocate that. Yeah. On the chip, right? Maybe this is input, that is output, and the compensation capacitor and digital circuit, blah, blah, blah. That is the so-called floor planning. After you do all the necessary layout, then we can extract the parasitics. For what? For post-simulation. I think I told you already. The major difference between pre-sim and post-sim is parasitics. If you simulate your circuit with all the parasitics you extracted, then it is for post-simulation. Okay? But even after layout, you can do the same simulation without parasitic. Then forget about it. The result should be exactly the same as the pre-simulation. Okay, so, okay, one moment. After layout, after such kind of extraction, we will have two files. Okay, one is the equivalent circuit, and the other one is the parasitic. Okay, for the equivalent circuit, it needs to be compared to your original schematic to make sure they are exactly the same. That is so-called LVS. Layout versus schematic. Schematic is original circuit you draw. Okay? So, how to compare this to that? Only Apple can compare to Apple. So, we compare the equivalent circuit of your layout to the original circuit. That's it. And they need to be exactly the same. Exactly the same means what? If you simulate your equivalent circuit or your original circuit, they should be exactly the same, with exactly the same performance. So what is the difference here? Parasitic. With parasitic means what? Post-simulation. Without parasitic means pre-simulation. Never mind, you simulate the equivalent circuit of your layout or the original circuit. They should be exactly the same if there's nothing wrong. Okay, so please keep this in mind. After extraction, you will get two circuits, two packages. One for equivalent circuit, it should be exactly the same as your original circuit. Never mind you simulate it or your original circuit, they should be exactly the same. The only difference is the parasitics. That's it. Okay? But why I need to mention this? Sometimes that is such kind of good understanding can help you speed up the circuit simulation. Yeah, especially for your circuit, you have analog part, you have digital part. Usually, the number of devices for digital part is much, much more than analog part. Okay, who controls the accuracy? Your analog part. But who dominates the simulation time? The digital part. Because for maybe adder, right, counter, okay, flip-flop, well, they have many transistors inside. Or even a flip-flop, usually for the traditional one, static one, more than 8 transistors. How about your op amp? Less than 8. It doesn't make any sense. Again, op amp, most of the analog devices, they dominate the accuracy of your circuit. But in number, they are much less than the digital part. For simulation, your SPICE is not so smart. They treat one transistor, never mind the digital one or analog one, the same. Okay? They spend the same effort to simulate your digital transistor and your analog transistor. It doesn't make any sense because it wastes a lot of time. So, in my class, that is one of the key differences because I was an analog IC designer. I designed my own chips, and I taught my students to do a good enough design. I'm much experienced. I would like to share my experience with you. So, how to speed it up? Again, after layout, you will have equivalent circuit for your analog part, equivalent circuit for your digital part. Okay? Yeah, and the parasitic. The parasitic. Okay? Your simulator will waste most of the time on such kind of parasitics. How to speed it up? Because I told you, it dominates. And maybe also this. Yeah. The analog, equivalent circuit, and parasitics, they dominate the accuracy. And this one only slow down. Usually only slow down your simulation. Okay? So how to speed it up? Forget about this. Bingo. Exactly. Okay? Maybe you will be curious, how can I do that? Okay, you can separate your circuit into two parts, analog and digital, right? Analog, after layout, with the equivalent circuit and the parasitic. And how about digital part? You still use the circuit for your pre-simulation. Good enough. Good enough. Okay? In this way, you can speed up very much your simulation. After you make good enough result, then for the final run, yeah, you include the parasitics of your digital circuit. That's it. To make sure your digital circuit can drive your analog one. Your analog circuit can drive your digital one. That's it. The interfacing with the parasitic of the digital part, you would like to make sure interface between analog and digital is correct. That's it. All right? Please keep this in mind. Then your design will be much faster than the others. If nothing wrong, we can go for fabrication, and after you get the chips, we can do the measurement. And usually, yeah, for the new student, for the new design, right? After they measure the chip, they will say, "Wow, so bad," or even not functional at all. Okay, that is your case. So, what is the practical thoughts about such kind of op-amp design? Experience is a great help, because from the very beginning, you need to choose, hopefully, the best one, the most proper one for your application. But it depends on your experience. Okay? So hopefully you choose the one meet most of the specifications for your own application. So it is application oriented. Okay, case by case. For this case, maybe this op-amp is bad, is good, is the best. For that case, oh, it is really bad. You need to choose. You need to select the other op-amp. Blah blah blah. And this is my sincere warning. Don't create your own. Again, why? There are very few op-amps existed on Earth, simply because for all the others, they are nonsense. Okay? If you create a new one, I cannot say congratulations. I promise you, with 99.9999%, it's nonsense. Okay, it doesn't work at all. Alright? So, even for a very experienced analog IC designer, they choose the typical one and then modify a little bit. That's it. That's it. Okay? Don't believe in yourself too much, because from the history of humankind's design, we prove it already. Almost 100% of the new structure is nonsense. It doesn't work at all. All right? And then, according to stability, you need to determine what kind of compensation you need for such kind of circuit or op-amp. Right? According to how much load you need to drive, and how much stability, especially phase margin. How large the phase margin should be. And usually we apply meter compensation. That is really interesting, right? Meter effect usually is a bad, how can I say, is a bad consequence. Yeah, as I mentioned already, from the input to the output, right? This one will be increased substantially. We hate it because it will substantially reduce the bandwidth of your operation. Okay? Okay? That is the bad. But sometimes even the bad can do good things for you. Yeah. For compensation. So what is the major concept of meter compensation? This one will be enlarged by, what might I say, equivalently. Okay? So, if you face the challenge, then apply this concept for your compensation. Usually for compensation, we need very huge capacitor. This is too ridiculous. So we can apply meter effect to increase the effective capacitance. Right? Right? That's it. So for example, if A is 100, yeah, what does it mean? The real capacitance can be reduced by 100 times, because it will be increased by minor effect for 100 times. That's it. Okay? So, there is another lesson for you here. Never mind the phenomenon is good or bad. You need to know all of them. Yeah, sometimes even the bad effect can do you much goodness. Okay? Yeah. After you choose the right one, then you need to do your own design, the DC bias, the device sizes. Yeah. In theory, it begins with hand calculation. We have a lot of equations from your microelectronics, from your analog IC design textbook, never mind from Allen or Razavi. But to be honest, who did such kind of calculation? Almost none. Nobody. Okay? Usually, we don't calculate. We just do it by trial and error. That's it. Okay? If you're lucky, you can copy and paste the op amp designed by your seniors, then do minor revision. Otherwise, when you read analog IC design papers, usually we have only circuit. We don't have any sizes, we don't have any bias. You need to guess. That's it. You need to try by yourself. So, do you need to calculate? Oh, yes, in theory, but in practice, even for myself, for my juniors, for my seniors, usually nobody does any kind of calculation. We depend on our own experience. That's it. Okay? So, we depend on the simulator, I mean HSpice, iSpice, to fine-tune the circuit. That's it. So, the first cut, yeah, that is from, in theory, calculation, in practice, by intuition, okay, by guessing. You guess, oh, how much it should be, blah, blah, blah. Okay, and then go for optimization. Yeah, it takes the much longer time for such kind of optimization. But we need to face more challenges now or into the future, especially for such kind of low voltage processes, because for such kind of new processes, the output conductance is too much. Okay, output conductance is large. It means for digital circuit with larger current, they can operate with higher speed, right? But large GO means smaller RO, right? That is really bad. And how about GM? The same. GM is reduced. Why? According to early saturation. Okay, that's it. According to early saturation for such kind of very good processes, GM is reduced substantially. Yeah, much less than your imagination. That's it. Because for new processes, you will say, hey, look, W over L, the L can be very small, right? Forget about it. Yeah, because for early saturation, the square disappeared. You get only one first order instead of the second order of VGS minus VTH, right? So what you lose is much larger than what you get. And this is the reason why GM goes down very quickly for new processes. And also that because the supply voltage is decreased, then some of the very good structure cannot be applied anymore. What? Cascode. Okay, because with such kind of low voltage, usually cascoding cannot survive because the headroom will become almost zero. Oh, no. The output swing will become almost zero. It doesn't make any sense. Okay? Yeah. It will seriously limited your input and output swing. Swing, 秋千, 荡秋千, 摆荡幅度. Yeah. So it means, yeah, how large you can operate, what is the range you can operate. We call it swing. Never mind for input or for output. Okay? Yeah, you can guess. The lower supply voltages for both input and output, the swings will be reduced. Okay, that's it. Yeah. So I need to warn you, many of the existed very good architectures, they cannot survive in such kind of very low voltage processes. Okay? Yeah. And then we need to get help from the so-called analog friendly devices on your chip. Or you need to go for analog friendly processes. It means old processes, just like 0.18, 0.35, 0.25. Oh, they are really large, bulky, right? Yeah. If you apply analog friendly devices on new processes, wow, what does it mean? Yeah, hey, for your 19 nanometer, or even I guess for 20, 28 nanometer, they still can provide some transistors, yeah, functional under 1.8 or even higher supply voltage. Okay, but for the size, there are for 1.8 volt MOSFET, the size I guess is about the same as 0.80 micron, right? So the same size of the transistor for 0.80 micron or for 20 nanometer. For 20 nanometer, it will cost a lot of money. Okay, even they are all the same size, the same performance, but it's really expensive for the new processes. Okay, so it means what? Such kind of analog friendly processes or analog friendly devices, they are not a long-term solution. Sooner or later, we had better get rid of such kind of analog friendly devices, analog friendly processes. Yeah, but how can I say? Till now, we still don't know how to go. Yeah, maybe in this chapter we will show you one way out. Okay, but your brain needs to be washed after you go, before you can go further. Okay, so we need new approaches and new architectures. Yeah, hopefully we can take advantages of the new processes. For example, the unit gain frequency is much higher than before. Okay, new processes, right? So you can see the MOSFET can operate much faster than before. But I told you already, according to GO, much larger GO, they can operate very fast. But according to RO, that is really bad for your analog voltage gain. And also GM is decreased, is degraded. Yeah, so hopefully we can take the benefit, enjoy the benefit of process scaling, but we still need to achieve high gain. That is really hard for voltage. For current, maybe it is possible, but for voltage, it's really hard. And you say, hey, I can get good enough I/O, then why not we can get a high enough voltage, because RO is degraded very much. Okay, anyway, we hope we can, under such kind of new processes, low voltage, we can still achieve enough high gain, yeah, and also fast settling performance. Okay, yeah, that's it. Maybe we can have a break right now. Allow me to get my coffee. Then it starts the brainwashing. Since it's this page, very important, don't miss it. Thank you.